All right, why don't we go ahead and start, since we're likely to be a quorum right now. Morning, Ash. Looking like you just woke up.
Me? No, this is just my hair. Just got back from Home Depot.
Wow.
A whole bunch of stuff. New house, so
moving in.
No, we moved in end of January. That's this. So this is my loft.
Mm-hmm. Nice.
Yeah, it got the dream house in Miami.
Super.
Yeah, but now for jobs, might have to move myself though. Facebook, for instance, requires, if you're an independent contributor, you can work anywhere, but if you're management in any way, you need to work in Menlo Park.
Yeah, work is changing, but it's not, but there will be some jobs that require you to be there.
Mm-hmm.
But I think in general, there will be lots more jobs that are just untethered. You can just be wherever you want.
Same with Microsoft. The role I interviewed for, that I'm being considered for, that one also requires relocation to Redmond. So yeah, I bought the house for the family, let them be all nice, safe and all that, while I have to probably get my own place over there. And hey, we lost Mayank.
We did. Let's see. So I guess while he's coming back, I had no plan for this class because I thought Mike was going to be here, but I think what we want to do is we want to go through that extra auto diff notebook in the repo. Let me
ask, when shall we go over the deep learning part of the Geron book as a review? The way we did machine learning part, which was really fun and interesting.
Yeah, we have only one more session to do that, and that's Wednesday.
Okay.
And then we're off Monday. Sorry, we're off the following Sunday for Easter, and then the following Wednesday, I believe that Wenchang is going to kick off his Wednesday night productionization. What does he call it?
Operationalization. So
pipeline, pipeline and production, yeah, that kind of stuff. And then the following Sunday, we kick off our reinforcement learning study group. So we have one day after this to catch up.
Can I share about on Friday, they had an incredible conference. There are lots of great conferences, of course, as you all know. I know Mayank's attended a few. This one was with a startup that's grown very, very well. It's called Scale.ai. They're out of the Bay Area. Well, they got Francois Cholet. They got to speak about just neural networks and deep learning. They had Andrew Ning, Jeremy Howard, and Rachel talking about how they built up fast AI. They had Somit Chintala talking about, who was brilliant, absolutely brilliant. So Somit was the guy who developed PyTorch.
PyTorch, yeah.
And he talked about, well, the new framework and how PyTorch is going to evolve. And he spoke very, very well. And he walked through, it was an excellent presentation. So I would strongly urge folks, look up Scale AI on their Twitter feed, as well as on their LinkedIn feed, to see when they'll make the recordings available. Some of those sessions were brilliant. Somit's, Jeremy's was, typical Jeremy and Rachel. Somit, Andrew Ning had and so the big takeaway really for me was the pipelines operationalizing, using whatever method you want to use, Kubeflow, whatever, the whole pipeline for building a solution. While also remembering, it is really about the data. So it's not the models that are really important, it's the subject matter expertise around the data.
Yeah, I heard Andrew Ng talk earlier this week. He gave a talk online, and he was talking about ML ops, and he's saying how ML ops is now a new field, and it's data centered. It's like you don't you just keep the models you have, and you figure out what you can do about the data. Like, the simplest thing is getting more data. The other thing is, augmenting the data, making it clean, getting rid of dirty data. And he says that's where the next level of improvement is going to come in models. And yeah.
Yep, that is exactly what he said. And so
really,
yeah, it was absolutely brilliant. And that is really what all this is about. You've got a lot of enterprises and consulting firms that are trying out saying, hey, we've got these pretty interesting use cases. No one's buying. No one's interested. It isn't about those simple, fun use cases. Companies already have people, even if they're not titled as data scientists, they know how to build these things, especially the better, more talented IT folks have focused on the data engineering ML ops side. They've evolved their DevOps skills to more ML ops, and they're helping their employers build those pipelines and full end-to-end solutions. So exactly everything, Andrew, what you just elaborated on, that is really the way we need to start thinking. Those were the conversations that Wenching and I had, and he was very eager to do that class that he'll be starting soon.
I think Mike has rejoined. So I shared this link to the to that extra AutoDiff Colab notebook. That's probably what we're going to focus on today, right? And I know that, let's see, Mike, you posted a video.
Yep.
Do you want to tell us about that?
Yeah, that's basically a way to so I posted two videos. One was a geometrical introduction with respect to how the gradients flow. Uh, uh, that was a geometrical introduction to partial derivatives with animated graphics. It's much like the three blue-brown videos that we see, but it's intuitively had some valleys and crusts that most of the folks miss. And it's more of like airflow stream kind of a uh, plane. So yeah, that's one good example too. Uh, the second one was automatic differentiation, in which we used gradient tapes and Hessians and that's, the second order and the first order, and how can we persist it, and a couple of other techniques to uh, do that, to uh, have those gradients. But yeah, we will do them and take a
Why
look
don't
at.
we, why don't we just go through, why don't we just take time? The videos are a total of about a half an hour. And I think, what if we all just listen to them and then come back together after that and talk about them?
I was thinking more about showing you guys the code, and we can take a look through the code and go through the code to get a view of how actually it's working. So
The code for chapter, the code for that section for the
yes, yeah,
in the notebook.
yeah. In the notebook, that will be much more intuitive. Yeah, that would be fun.
Okay, let's do that then.
There was that too. Yeah. We had 4 techniques that our text had defined in the auto diff notebook: the manual differentiation, the finite differentiation, the finite difference approximation, the forward mode autodiff, and the reverse mode autodiff. So let's take a quick stroll through the text here, and then we will go through the notebooks. That would be fine, I guess. Uh, this is uh, uh, they don't use this function here, f(x, y, x squared y plus y plus 2,
Are you
and the
sharing?
partial.
Are you sharing your screen?
Yes.
Yeah, I can see as appendix the auto diff, and
Okay.
Mhm.
Yeah, I see it.
Mhm. Um, Then, yeah, we had a manual differentiation. When the last time that we talked about the MASH uh, uh, derivation of the sum of those derivatives, how do we uh, find out the sum of functions, the sum of those functions derivatives, and then the derivatives of lambda times the function, the ways to use them, and to uh, uh, the rules that we had, the simple rules that we had seen last time in the notebook. This is then look at
Can you make that screen bigger? It's the text is really small.
okay, this one.
Yeah, that's better.
Can you
That's a
guys?
little better. That's a little better. Yeah.
This is really good. The online learning portal of Morale. That's a kudos to them. Kind of manage this in such beautiful way. But anyways, so this is the manual derivations. These are the 5 basic rules: the derivative of the constant, derivative of multiplied by x, this guy here, uh, uh, the squared, the derivative of the sum of functions, the derivative of lambda times the function, this guy, the partial derivative. Then they have used the simple partial derivative equation to find this out, and the tedious for the complex function. The risk of making mistakes and define it different, and then we take a look at the finite difference approximations here. So yeah, these are those points as we have seen last time with respect to graphs of how those plot. They are uh, trying to find out the limit of the slope of the line, which goes to the point x naught and another point x on the function. And when as x goes infinitely close to x naught, how does that uh, give us the uh, limit here? This is the definition of the derivative. And mm, this is just the basic. Uh, this I think so are using dual functions. Calculate, yeah, the with respect to epsilon that is being added, which we will take a look at in the later part of the section. This type of numerical approximations are called finite difference approximation. This is Newton's difference quotient, and this is the simple code with respect to the equation that we formed and the derivative. This is simple forming the results that we get. This is the number of times that we need to call. Call f at least 3 times, and it could be optimized, but if it was 1000 parameters, we will need to call it 1001 times. So this is the naive way that we can. This is the basic, the most naive way that you can do the this finite difference approximation in when we do it in code. So it has a flawed technique to train or scale with respect to those large neural networks. And then we turn on to AutoDef using the forward mode. We have used this figure here with forward mode. This thing. So there must be a figure here too. Let's see, figure or what? Can you guys confirm? I think my browser. Figure D1. Is there a figure?
Yeah.
Okay.
Let's see. I'll get a screenshot of it. Okay, I'm gonna post it to Slack. Let's see. Okay, it's in Slack.
So this is how the forward mode AutoDef works in the system. Now, yeah. These are the leaves that we had with respect to the equation that we represented. So 5x, 5 plus xy. This is 5. This is the node which is taken as the representation of those addition and multiplication as well as division. And I think so powers and all that stuff too. Those are all those what we call the basic mathematical uh, uh, functions, if I'm right. I do not. know the exact term for that. Yeah, this is the basic graph that we could construct. And then this is a simple forward mode autodiff in which we get a graph on the right, which represents the partial derivative of this guy here, f5 plus xy. So this will be 0 plus 0 cross x plus y cross 1, which is y. So yeah, for each term in this leaf node, we get a um, extension of the context that of those uh, from the initial graph that we constructed on the left. So here, okay, yeah, here you can see from this guy to this guy here that we go from this guy to this guy with respect to those um, uh, value of x that we the partial derivative with respect to x that we calculate. Then from this guy to this guy, this can be extended as this. This is the chain rule. Constant will have a derivative 0, and this guy will, yeah, represent this. This is a simple representation of the partial derivative that we obtain with regards to y. This is the forward graph that we construct. Moving on. This is with respect to y. Y is the function here. So sorry, this is with respect to x, and we can get a similar graph with respect to y2. Then, yeah, it starts by this process is explained as I've just shown this in these two paragraphs. The multiplicative node, it calls this by this chain rule, and then the addition node, and then we sum it, and then we get the correct partial derivative. Uh, then we have a much smaller graph with the right node here. Then uh, this will have a suboptimal performance because to construct a huge graph, we will have to go through one node at a time. And that will create issues. And and there are multiple other factors too with respect to the memory that is required and the computations. Uh, so next they have, so this is a kind of a computation graph that they have highlighted. This is the symbolic differentiation, which has two nice features, which gives first the computation graph of the derivative has been produced, and we can use it as many times to compute a derivative of a given function for any values of x and y. Then the second reason was the forward mode autodiff. Uh, on resulting graph, and we can get a second order derivative and so on. So yeah, we can do it multiple times. Then in this paragraph, they have defined the use and defined a way to use this without constructing a graph by using a dual numbers. This is simply a form of adding an epsilon value, which if squared is uh, small, such that it reaches zero, but it's not exactly zero. So the epsilon value here could be 0.000024, and if we square it, so yeah, that will reach some representation of a squared value which approaches zero. So that's that. And if we have a 42,74, it can be represented as this guy, as this pair. Since three operations with a dual number, this, and this. These are the operations that we can use. It's simply a basic calculus here that we have. Then we can compute the most importantly, what they have shown is we can compute both uh, uh, the first order, that's the derivative of the h prime a in the h dash a in one shot, as well as the h of a. So yeah, we get both of these results. And that's the upside to it. So that's why we are using this. And then we have those dual numbers whose first component is equal to f3, 4, and the second component is equal to df by dx3, 4. So these are the two numbers that we have taken. So if we forward mode with two numbers. Now here also we can see this x. This is the value that we need to compute. This is the compute the f of 3 plus epsilon, 4. So x can be here. X is taken as this guy and y is taken as this guy. This is squared. The equation was x squared y plus 2. So if we put it here, x squared y plus 2. So this is the equation. Yes, we can take a look from here, right? This is the equation. Yeah, this guy x squared. Then this, since this is 0, plus y plus 2. So yeah, this is how we get it. So yeah, it's simple graphical way to show those nodes, and yeah, these are the stored as a pair of loads. not as this guy. These are the assumptions that we take when epsilon squared is 0. So that's why we have used this. This was it. And we have those views that has to the number of parameters and the number of passes that is required to compute all those partial derivatives. Yeah. So this is the compute that is required. Mm, it requires 1,000 passes, but if we go to the next step, that's the reverse mode autodiff that TensorFlow uses. It can compute all of them in just 2 passes through the graph. 1,000 versus 2. That's the magic. And reverse mode autodiff, yeah, that's implemented by TensorFlow in the reverse direction to compute all the partial derivatives. And with the gradient flow is in the reverse. This comes from the second pass when the gradients flow in the reverse direction. And during the first pass, the node values are computed starting from x equals to 3 to and y equals 4. And then we can use those values from this guy here. After those have been computed to use them, and yeah, so it's a kind of a differentiable programming paradigm. Sorry. Uh, Dynamic programming. I'm mixing this up. Simple, yep. It's a dynamic programming paradigm in which we reuse them. Yeah. We calculate the output nodes here with respect to the. So here, each and every node has N1, N2, N3, N4, N5, and N6. These are the nodes and the classes that we have. We will see the approach of how can we construct this in the notebook here. Then
it seems peculiar that he hasn't defined, it doesn't look like he's defined F anywhere, or at least I haven't seen it.
The F function here.
I think it's x squared y plus 2, but he never explicitly says that.
He hardcoded, right? So he's specific. So this only works for the function x squared y plus 2, right?
Yeah.
X squared y plus, it's x squared times y plus 2, I believe.
Yeah, x squared y plus 2. It's given at the top. This is the function that they have used. The four.
At the very top. Okay.
Yeah. So on the right too, if you can see, this is the function x squared y. I've highlighted this in blue.
I see. Yeah.
Then N7, this guy. Yeah. So they reuse those node values. Yeah. We get those values here. We can take a look at the graphs here, how they are computed, the df by dx, n1 cross 4 plus n1 cross 4, plus n1 we have here 3, 12 plus 12, 24. This is the df by dn2. We will get here 9 by df by dn2 plus 1 here. This will equals 10. This is the flow of the values that we get. It's a kind of
And this is not making sense.
this is with respect to the chain rule here. So if df by dx can be written as df by dni and dni by dx. So n7 is the output node, then f of f equals n7. So df by dn7 will equals 1. So here in this case we are adding this dn7. In the n7 we have these the output node f here is this guy here, which has this value.
Well, like when you look at df by dy in the middle on the bottom, df by dy is df by dn2 plus df by dn2 equals 9 plus 1 equals 10. That doesn't make any sense at all.
Oh, yeah. From that perspective, but this df by dn2 and df by dn2, which has those 1 and 2, these are coming in from the left and from the right. So yeah, df by dn2. So here it's this value is 1, and from here, if we take a look, it's 9.
Okay, it's flowing. Yeah, the derivative, the derivative is
Yeah.
flowing downward. Yeah.
Yeah, the reverse ordered, so from the top to the bottom. So from that sense, this, 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 then from this guy here, it is going through here. 1, df by dn7 and dn7 by dn5. dn7 by dn5. dn7 by dn6. The second part doesn't make sense. Do I think so? Yeah, this must be some constant, or I'm missing something here. Since n7 simply, we already know df by dn7 is 1. df by dn7 is 1. And dn7 by d, we know that, but this guy, dn7 by dn5. So since n7 simply perform the sum of n5 plus n6. Okay, okay. 5 plus n6, then we can get from this that dn7 by dn5 equals 1. dn7 by get that dn7 by dn5 equals 1. So d5 df by dn5 equals 1 cross 1, which is 1. Yeah, this makes sense. I hope it's clear how we this is from this term here, and this term is a summation of this plus this. So yeah, we get this one here. Since n7 simply performs the sum of n5 plus n6. The classical dynamic programming. Then how there is a query which with respect to how much does f vary when info varies. The answer is df by dn4. This then we similarly get this guy. 1 cross n2, which is equals 4. This is simply the so yeah, we can calculate those values. Partial derivatives. In the end, we find that df by dx is equals 24 and df by dy equals 10. These are the values that we get. And we talk about the uh, reverse mode autodiff, very the advantages of it with respect to the other uh, techniques that we have discussed. Why graphs use this um, to backpropagate the gradients. Uh, Reverse mode autodiff can handle functions that are not entirely differentiable as long as you ask it to compute the partial derivatives that are differentiable. Okay. Uh, uh, that's cool too. Then exactly how does this work is it implements the symbolic reverse mode autodiff. If how does TensorFlow implements it? It creates a new computational graph here. So this is implemented, and then the computation graph builds the laws with regards to the parameters, and this executes over the stuff again. And we can compute the higher order derivatives to if needed. Yeah, this is the whole example. And then they define it with respect to the function. If we need the input function x equals x squared, then we need to provide the corresponding partial derivative, that is f dash x will be 2x. So yeah, and then it will automatically find this guy here. Now let's look at the same code. So this is the function. that we wanted to fx comma y, that's x squared y plus 2, and then these are the parameters. Let's have this. Yeah. Manually, we will solve it using this with respect to x and with respect to y, and then this. This is the partial derivative of this that we give the code. This is with respect to x squared plus comma x squared plus 1. So this is with respect to x, and this is with respect to y. So then we have this df 3 comma 4 that we call. We get 24 comma 10 as those values. Okay. Get those values. Then we get the equation for the second order derivatives. These are the Hessians that we have. Then we define it here. Respect to the dx. This is the first one. We have 2y. The second is 2x. D2fy dx or dx dy. We can define it as this, and we have 2x, and then we have a 2x and 0. So these are the values that we compute them, and we get these. And this is at the most basic level of how those things are calculated in code. Then it's practically impossible to compute derivatives this way. Then we look at the ways to automate it. We define a function gradients where partial derivative is a list, empty list. Then we have a val list of functions. It's a kind of args parameters that we have. We take the range of this lengths and we add it to those lists. This is tweak variables idx plus this guy. This is a representation of those um, variables, and this is the epsilon value that we take. This is a very small epsilon value. Then we have a kind of a derivative on this formulation. Then with respect to those in this list, we append that, and then we return this. So this is the gradients function, and we do all these steps. Yeah. Here, when we call this in a df of x comma y, and we pass in the function and the list, the variable list, can get it, can get the values here. Redirect. So these are the values that we get. Then these are the Hessians, and then we create a function that computes the first order partial derivatives. It's called the Jacobian. For the first order calculations, we just need to give for df by dx and the df by dy. So the zeroth and the row. I think so. It's if stick zero. Okay, okay. We only take the zeroth element with respect to since the f of the function with respect to x here, and, and the partial derivative with respect to x, and the second is the partial derivative with respect to y. So yeah, these are the two rows that we have added, which we appended here. So yeah, so we can have 3 variables, 4 variables, and yeah, we will have to take those number of. Then we apply those gradients function. This is interesting. We return df by dx with respect to 3 and 4, and the gradients of df by dy with respect to 3.4. And then we formulate this. Value that we get here is this is with respect to x, and this is with respect to y. So this is the Hessians that we calculate, the second order. Last time I had a query with respect to where the first order functions are useful as against to the second order, or the n-1 order is useful as opposed to the nth order. And if we take a look at convolutions, the convnets, and those script connections that we have in some of the architectures like units and vnets, there with respect to the sharpness of an image, if we have to get particularly sharp image, then uh, those first order uh, 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 um, uh, and calculations or the derivatives are useful as compared to the second order. Because the second order will represent in a much noisier, or those pixel values will kind of distort, as we had seen in the EBM lectures.
I'm not sure what point you're making right now. I'm sorry.
That was with respect to the query that I had of why in some ways in computer vision specifically, why would we use the first order derivative as compared to the second order in via if we have that loss function. So in those script connections that we had, U or V networks. While formulating that loss function, we kind of propagate uh, uh, those pixel values, those uh, through the network without going through the lower layers. So those skip connections are kind of needed to provide that kind of a sharpness. Last time I had a query with respect to which cases do we use them. Was a answer that I kind of came up with. So I think so. Maybe I should open up the figure. So here was looking at this. So with respect to passing those skip connections while having those latent representations, or can we have those sharpness values to be uh, consistent or well formed while the outputs are proper. If we try to generate those images from the latent space, so that's the up convolutions, and this kind of presentation in an architecture with respect to the loss function will help in those sharpness of the image as opposed to the
Right. I guess the
blurriness.
question is, what does this have to do with the Hessians, the discussion that we were having about Hessians?
And this was with respect to, I think so. How do we like in mean squared error versus uh, normal mean error? How does that differs? This will have an impact upon the representation of those uh, variables, and how do we tweak them. So uh, this will totally impact our uh, approximations. I was thinking from that terms. If we have to get an approximation with respect to the second against the first, and we're trying to model specifically in vision. This is the problem that most of the folk uh, face, and why those skip conditions are needed.
Yeah, but this is about Hessian. This discussion is about Hessians, and I don't see the connection with skip connections. I mean, in gradient descent method, we're always working with the first derivative. We never worry about the Hessians.
There are specific cases in which we go down to the second derivative too. We will take a look at them in the advanced Autodiff. There's a couple of notebooks that I borrowed from the TensorFlow guide, and there they have defined the second order TF gradient tape, that those context information that they use, and how can we use how can we practically implement it in uh, in view of our application. But yeah, those I agree. Those skip connections are a total tangent as to why we use it. I borrowed those ideas like since they are computationally as well as kind of feature wise, they give a good value to our the presentations from a image. Oh, I thought, why not? It's a kind of a tangent. I agree. Then we have a kind of implementation in the toy computational graph where we implement this. This is the symbolic autodiff technique that we are implementing. We have defined two base classes, the const and the var. We have extended object here, and each has a evaluate method that is used to return that value. The init and the string to just represent the uh, uh, initialization and the name. And then we have three operators here. The binary operator, uh, which is the base class, that is extended by the add and the multiply. And we give a representation of these two guys here. The self dot a dot evaluate plus this add binary operation takes in a simple uh, 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 variable and adds it up, while the multiply will take this variable and multiply it. It's simple really with respect to the graphs that we have shown earlier. So, yep, this. Then we have a computation graph. These are the basic components that we have. And then we build a computation graph to represent this function. This is the x variable, this is the y variable, and this is the f, the function that we define. Add the compositions here that we use, which the original function was x of x comma y is equals to x squared y plus 2. So yeah. It's a hierarchical representation of a constant and a variable, and those addition and multiplication operations that we have. And then we define the values for x and y, and then we use the evaluate, which gives the value here, which is respect to this guy. Here we get also had the evaluate function, which will give 42. Okay, yeah. just why this represents something else. No, that's next. Then we compute the gradients. This is a representation of the composition. We have the Z equals V of U of X, which we rewrite as this guy here. Z V of S and S U of X, and we get the chain rule to apply the partial derivative of the outputs with respect to the input X. And this is this. Which we get intermediate inputs. So this is the same representation that we had. Then what they do is in the forward mode autodiff, these the algorithm computes this term forward in the same order as the computations required to compute the output Z. And in the reverse mode autodiff, they compute it backwards, the Z and the Sn, and then from d of Z, d of Sn by d of Sn minus 1, and so on. Yeah. Then we need to compute those derivatives as a function of this guy using the forward mode. And then this is the representation of an example of how they would go step by step. Then they verify the results that they have defined earlier by this. This is the simple with respect to the Z and the 3 is the value at X equals 3. This is the function sine of X squared. We get minus 5.4676, which is the same thing. We get this here. Then, so this is clear. This is the manual versus the gradients that we had defined. The gradients function that we had defined earlier. Then we use the same thing using the reverse mode autodiff. This was in the forward. Start from the right hand side, so we compute it using this guy. Sine S1 divided D S1 and cos is minus 0.91. Next, we will compute ds1 by dx dot dz by ds1 with respect to dx. Then we take this guy, which will equal to minus 5.46. And then they go on into the nitty-gritty of the computational aspects of how many steps that are required to compute the partial derivatives. Why do they use reverse auto mode? The right mode, most terms can be computed just once. and used to compute all the partial derivatives. That's the reason. So, so majorly reverse mode autodef is used here. Yep, this is ds I plus 1 and ds I that is required. This is a problem here with respect to the reduction of the number of layers in neural network. Yeah, this is also with respect to the memory footprint and how can they calculate those intermediate values. Uh, yeah, uh, this there is a particular way in which you can use compute cycles for the VRAM in the GPU. That's the paper that they represent here. This was in 2016, memory efficient backpropagation through time, which they use this divide and conquer approach. They define a kind of a computational trade-off policy. I think so, yeah. They use this word here. Illustrated the optimal policy for m equals 4, with t equals to 4 and t equals to 10. That these are the time parameters. Here they have used the 10 steps, and here they are used the 4. And what they do, this is a kind of a dynamic programming objective that they have defined. This, yeah, we can go into the details too. Just, I think so. They have shared this link here in the yeah. You guys can check it out from here. This is an interesting read.
This is RNNs, right? It's back propagation through time, so it's RNNs.
Yeah, RNNs, but similar kind of methodology is currently being applied. So, yeah. Because this uh, can be unrolled in a form of RNNs in a way too. So yeah. Then they give a forward mode autodiff version of the same thing, in which we have manually defined this gradients. Yep. So as we have seen earlier, uh, we had four classes: const, var, add, and multiply, and have we are adding a gradient. Uh, we are adding a gradient as a lambda layer here with the variable and the self, which is the class object of the representation, and we gave the values here. The constant 0 in the case of variable, it will present the constant one if itself or is kind of a variable or else const 0. And then we have uh, addition in which we pass in the add function with respect to those self.a.gradient because a will always be a kind of a constant or a variable. So, and then this lambda is with respect to the multiplication. So add of the multiply of a and the gradient vector of y plus the gradient of var multiplied by the b, which yeah, that's the expanding rule. That's what they've defined here. Then these variables with the initial values we use, which we give as x and y and 3 as 4. And then we define it. Those function, that's this guy here. And then we calculate the df by dx and the df by dy, which is x and y, just 2xy, x squared plus 1. Yep. This is it. So this is the gradient here, and then we evaluated it, and we got those 24 and 10 values. This is the way of the forward mode autodef. I think so here also he had this 24 and 10. I think so this we had, this is a separate computation, I think. Yeah, it's separate. But I thought they had taken the exact value here. This they have taken as 3 and 4, and what they taken here. Yeah, this is a separate function. So the 42 and 24. We have df by dx as 24 and df by dy as 10. Okay, so yeah, we have used this and got these, and then we compute the second orders, and the values that we get are 8, 6, and 6, 0. The second order which we compute are with respect to dx, then dy, and the dx and the dy on the first order derivatives. This is just approximation. Then we go in using the dual numbers, which we had alluded to earlier. If this is 0, we can ignore it. The epsilon square. And why we do this? Because we can use this equation and we get the value of this and this. Then we have this addition, subtraction, the multiplication, the division rules, this power rule that we define here. This is the dual number here. respect to cell dot this guy, then this guy. We define those in addition, multiplication, right multiplication, the string. This is the simple representation of this vector in this representation. And then we have class method to the dual, which uh, has an attribute, and we return L or return this parameter CLS. This is with respect to those we had. So this is the value that we get. Three plus two numbers. Get it as this guy. And then we define. We have simple multiplication here. And we define the operations as this overloaded method. This is the right multiply, I suppose, yeah. And this is the computation framework that we get x comma x dot value and a y dot value. This we evaluate while we get our Torah computation framework, and we get this value x and y to x3 and y4. This is how we compute the partial derivative of f in regards to the x and y at these two values. We define this dual number as this. By value as this. And then df by dx is this guy here. We can present this. Df by dx will be 24 and df by dy will be 10, as we have gotten here, I suppose. Yep. This is the same forward mode autodiff, but using dual numbers. Yep. And then this had a limitation with only being uh, uh, implementable to the first order derivatives. But yep, this can be extended to the second and other order derivatives too, and the other higher order derivatives too. Then we have the reverse mode autodiff. Yeah, we get this guy here, class const, class var, class binary. We define those classes again and add here. In this case, in the case of constant, we are not using any application. Passing this. And in this guy here, we are accumulating those gradients. That's the difference between a constant and a variable. Then we have those add binary operators. Then we evaluated on the basis of this guy. The evaluation step is required for all the classes. Yeah. The backpropagation step was the gradient methods, how we would backpropagate it. So in the case of addition, we are simply calling what if it is a variable, then it will add it to that now will be cumulated. If it's multiplication, then this backpropagation will be multiplied with the uh, value of the uh, variable that we have, the A and the B. Yeah. So these are the basic steps that we take care of while trying to make our own reverse mode autodiff. Then we had this x and y variable of 3, 4. Then this function simple, and then the result, and then this f dot backpropagate 1 dot. That's the value that we have taken. And when we print it up, this is the x squared y plus 2. And the result we will get as 42. Yeah. The x gradient is 24 and the y gradient is 40. Yeah, it's the same.
I don't see where the epsilon was defined, because in the function, it's 0. In the dual number class, epsilon is taken as 0, and I don't see that changes anywhere.
Epsilon there bit is just it's in the first order. So here we are using the reverse mode. So reverse mode does not have the epsilon. We had it here.
I'm looking at the forward mode one where we define the dual number class, and in that class we initialize epsilon to be 0, but when we call that class, we don't change the value of epsilon. So I'm not sure, I don't understand how it's doing the calculation when it uses epsilon equals 0. I thought it needed to use a small number, not 0, to do a derivative.
Yeah. I think so here what they have done. So they called this particular method. They have taken the epsilon. They are taking epsilon as 1 here. When they have passed in value epsilon here as 1. So in the case of this statement here,
I can't see the, let's see. Oh, okay, there. Dual number 3, 1. Y is dual number 4.
So here they have taken epsilon as 1 instead of 0. In the case of x dot value, when we are trying to calculate df by dx, in the case of df by dy, when trying to calculate, they have taken the epsilon as 1, because that's the function that we when we expand it in the case of df by dy, that will have those two guys that we need to get value of. Like in this guy. So if x plus epsilon or if y plus epsilon, we have that. So in the case of x, we have taken the here at 1 when we need to calculate the derivative with respect to x. We have taken it by they have used the epsilon as 1 when we need to get the derivative with respect to y. So that's the two cases that they have implemented.
Yeah, it's just that, well, somehow they got around the approximation. In other words, in the previous cases, when we computed these partial derivatives, we didn't get exact values. But now we are getting exact values, and that's kind of like magic.
Yep.
Somehow, we never needed to use a small number for epsilon because of the way this works. And so I'm still trying to wrap my head around it. There's no place in here where we actually say epsilon equals 10 to the minus 7 or whatever. It just, you don't need that. And so it's very slick. The machinery is very slick, but I don't understand how it works actually.
Yep. For the large number of passes, I think so. Where we need to like this guy here, in which we have to cancel this epsilon squared. And the case of this, because this the forward mode with dual numbers is where it shines. The ways of in which we can get from a single statement, we can get both the function of that variable and the derivative on just one shot. That's the case in which it shines.
Yeah, but the amazing thing is that there's no approximation. It's getting an exact result in both cases, both forward and reverse mode. Whereas the when we defined, with the epsilon before, when we defined using the definition of derivative, we found that, we have to set epsilon equal to some, we explicitly set epsilon equal to a small number, and then our result is approximate. We don't get an exact result. So, but the mind-blowing thing about this auto diff is that it's getting an exact result in both forward and reverse methods.
Yeah, but this auto diff is, yeah, I totally agree with your viewpoint. But this auto diff in TensorFlow is implemented as a reverse, and I think so. If we go to some of the complex examples, then we might see some sort of approximation that's being applied. Because right now, I totally agree. These values are exact for the values of, because we are giving here it as 1. So I don't know. I think so. We will have to play around with this so that
I think maybe it's because the function that we've chosen is composed of, see, autodiff, it knows about addition, it knows about primitive operations, it knows about addition, and it knows about multiplication. So it knows how to compute chain rules and so on for those cases. And the function that we've given it is just a simple combination of those primitives. It's x squared y plus y plus 2. So or 2x, what is it? X squared y plus y plus 2, yeah.
Yeah, x squared y plus y plus 2, yeah.
Yeah, I wonder if
This is the this is no, the dual numbers here are 3 and 4. So it will be kind of, yep, this is the function that we have taken. So these are the values and the function here was that's why we get the same results. Because the results of those are being added and the addition and the multiplication is done according to the formulations of this variable. And since it is a toy, so this is in a narrow settings. So this is why this represents the dual numbers here represent these formulations. I don't know if because we are taking it here with respect to 3 and 4. So yeah, this is the partial derivatives that we get. For a higher number, if we go around, try to play with this. So in this case, we get a as df dy as 3431. It's over 10. So, but yeah, we get the idea. Since they wanted to make sure the graph from the book has the same representation as that of the uh, values that are reproducible in the notebook. So that's one reason why we have taken this example. Of course, for the implementation aspects, if you're trying to uh, use it in and industrial settings or some research work, then we might have to give a larger example here. But yeah, from the basic uh, learning perspective, this is pretty much great.
Now you can extend it with because he's given division and power formulas. So you could probably extend those dual number classes to include cases of division and exponentiation.
Yeah, totally agree. And those functions can have those representations as well. So yep, here then uh, uh, add, multiply, we might have a right division or right power and power, and we might use that to here. That will be good. Too. And some other log and other operations too, because they have not defined everything. Yeah, but yeah, this can be an interesting extension.
Yeah, and it's interesting that the this dual number notation is basically a Taylor expansion. It's defined so that when you take f of x plus epsilon, you just get the first order Taylor expansion. And the dual numbers are cleverly defined so that epsilon squared equals 0, which means that epsilon cubed and all other higher powers are 0. So, so f of x plus epsilon is just the first order Taylor expansion. And that's interesting because that's all you need to do stochastic gradient descent. You just need the first, you just need the first order derivatives. Sorry, the first order Taylor expansion.
That makes sense.
So you get this dual number out, f of x plus epsilon, you get this dual number out whose real or whose first component is the function and whose second component is the derivative of the function.
Yeah, but from a dynamic programming perspective, those reverse mode autodiff, I think so, will be much more beneficial. I don't know. For certain cases or certain examples, that might be, because I haven't gotten deeper into the differences between the forward versus reverse and the dual and without the dual. Yeah, that seems like a good survey paper. I think so. Most of the folks might have in the differentiate community have uh, had some sort of a established uh, uh, results. I think. Anyways, uh, moving forward, because so we are out of 9 more minutes. Wrap this up. This is with respect to the reverse mode autodiff. This so I looked at earlier. This guy. Yeah, and then we have the derivatives of x and y, and results. reverse mode autodiff using TensorFlow. TF variable 3, TF variable. We define this and as with gradient tape, we find the Jacobians. We get the 24 and 10, those gradients. We can compute the second order derivative and beyond too. There's this guy. We define the second order, and here persistence is taken as true because we need to reuse it. Here, the tape, since we have used it here once, we are reusing it. If we define this persistence as false, so we will only be able to use this tape once. That's the reason. And then we get the second order, the TF of TX. Then we delete this state.
It's interesting because he says that the way TensorFlow does this is it allows you to return just a string. In other words, just to keep it as a computation graph. I don't really understand this, but at the end he says this: everything is symbolic. He says that you can keep it in symbolic. There it is. Let's see. Right above a reverse mode autodiff using TensorFlow, he says, again, in this implementation, the outputs are just numbers, not symbolic expressions. So we're limited to first order derivatives. However, we could have made the backpropagate methods return symbolic expressions rather than values. This would make it possible to compute second order gradients and beyond. This is what TensorFlow does. But it looks like he's built in the ability to return symbolic expressions. Oh, but maybe not in the reverse mode. In the forward mode, you see in forward mode, he has this class dual number. And in that class, at the very bottom is this decorator at class method. And it has this method to underscore dual. And that method says if your input is a number, it has a value, then return the value, but otherwise return the string.
Now, because that string will have that epsilon embedded to it.
Yeah, and so if you, I guess, I don't think he used. Oh well, yeah, you're right. That's right. That's where he gets the epsilon out. That's how he gets the epsilon out.
Nothing so other than that.
Let me see.
Yes.
So I was thinking this was related, but maybe it's not. I was thinking this was related to the symbolic computation that he's talking about at the bottom, but maybe it's not.
Yeah, that's what I'm a bit confused about it too. And this is a class method with other than the cell. So we have this. What? This class method will represent yeah.
So I guess what this means is if you're dealing with, well, if it has a value attribute, then return that. Sorry. I don't know. It seems like if you're dealing with a purely epsilon number, then it just returns the string epsilon, I think. Class of n. Now I'm a little confused. I don't understand exactly what this what this
Dual.
class method toDual does.
A dual here, I suppose, the usage here.
Let's see.
So it's getting the value of that dual number. It's using this as intermediate to this is with respect to the right multiplier stuff. Okay, the right multiplier or the right add. That's the basic uh, here in the forward. We are using only addition and multiplication. So this is why this gives a representation here. And this is the right addition. I don't think so. We have used right addition here.
What do you mean by right addition?
Uh, right addition here. I think they have taken it from. I'm a bit unclear as to why the figure that you share this guy here. This is kind of a symbolic representation that we get. So this is the right addition, right multiplication that we are getting. And so this is why I'm still unclear of this stuff. Now, we'll get back to this and share it on the Slack.
Yeah, anyway, this is something, it needs a little thinking to work through these, this code, the last couple of, well, the dual number class and also the reverse mode auto diff. Anyway, it's a good place to stop.
Yep.
So
This is, I think so. Other than that, we have the gradient waves with respect to the second, computing the second orders. The df of dx with respect to x of y. So we will get these two guys, and with respect to y, and these four variables that are. No. Oh, this is it.
yeah, okay, so Wednesday we'll finish the whole thing by just all of us going through and reviewing the neural networks part, the second part of the course. I'm sure we won't be able to get all the way through it, but we'll get through whatever we can. Starting with chapter, I think we made it through chapter 7. So we probably, so there's some stuff even before the neural networks that we still have to go through, but we'll just get through as much of it as we can. It'll have to do.
Yeah. I will just like to point out to the 3-4 notebooks that are there in the guide section. They go a bit deeper with respect to the gradients and the gradient tapes. with respect to those forward passes. Since here, what the author has done is we have implemented most of the stuff in a custom way.
Do you have a link? Did you put a link
yeah.
to that? Is that-
Then we can here what the guide has done is gone into the details of
Okay, so we're going to break now and meet again on Wednesday.
Yep.
And would you mind posting the link to the thing you're looking at right now in TensorFlow?
Yep. I have posted
Yeah.
the both of those guides in the chat.
In the chat. Okay. Okay. Yeah. Okay, great. We'll just I'll put those in the Slack as well so that we can all look at them.
Yep. I think so. When you paste the meeting notes, I think so they get displayed.
Yeah, I'll just use those. I'll just include those two links as well. Okay. Thank you so much. And thank you for stepping up to do this last appendix. It's really good because I went through it the first time and I just read through it carelessly. I didn't really pay much attention to it. This time I'm trying to understand it. I don't think that I've understood it yet, but maybe with a little more work, I'll understand all of it. But anyway, it's much more clear. It's much clearer to me now than it was before, especially the idea that at least the way he's defined this toy thing, you get an exact answer out of both the forward and reverse mode auto diff. So that's pretty interesting.
Yep, totally agree.
Okay, everybody, see you Wednesday. I think Yuri was trying to say something, but I didn't hear it. So anyway, see you Wednesday, everybody.
Thanks.